Hey everyone, welcome back. In today's video, we are going to keep talking about infinite sequences and series, and we're going to start talking about series. So we talked about sequences, and we talked about how to take a limit of a sequence. That was all fairly trivial. Now, that's something I didn't want to go over just because we know how limits work, and we know convergence rules now. We know how to use those guys. So we really don't need to spend any more time talking about sequences just because we understand kind of the gist of them. Anyways, now we are going to start talking about series, and series are a little bit different. We're going to be spending a lot more time talking about series, and they're just going to be a lot more important to us in our study of infinite sequences and series. It's really just infinite series because we're dealing with what happens when we sum values and if they converge. So let's start talking about series. So we are going to talk about this in a pre-calculus sort of way. We're not going to be getting into the calculus of it yet. We will pretty soon. But a series is, honestly, it's just the sum of a sequence. So if I have a sequence that's like a sub n equals a sub 1 plus a sub 2 plus, no, that is what a series is. If I have a sub n equals, let's say 1 over n, I don't know, then our series is a sub 1 plus a sub 2 plus a sub 3, and then we can go on, so on and so forth. And similar to that of sequences, we can have arithmetic and geometric series. So if I have an arithmetic series, that means I'm adding numbers that have a common difference. And if I have a geometric series, then that means I'm adding numbers that have a common ratio. So that is what a series is. So that's a nice little review. Also coming back from pre-calculus is partial sums. And we are going to go back to talking about sigma notation a little bit in the context of series. We're going to be doing this a lot. Now, I think we may have covered sigma notation a little bit in the beginning of Unit 4 when we started talking about integrals and Riemann sums. But now we can talk about these things as kind of more calculus operations. So as you remember, we have an index, and we set the index to some starting value. So we'll call that 1 maybe. And then we go up to some ending value, we'll call that n, and then we do that of some a sub n, right? And just for, this might get confusing at some point, but we are going to, or sorry, not a sub n, we have a sub I. We are going to start, while we are using finite series, n is going to be the ending value, and I is going to be the index. But once we start dealing with infinite series, it's going to look more like this. We are going to have n as our index, and infinity is just going to be our ending point, and then we'll be a sub n instead of a sub I. But anyways, a partial sum just entails that we are summing to a certain number. So we're not summing to infinity, it's a partial sum of a series. So we're not summing the entire series, we're summing a little bit of the series. So the partial sum, the ith partial sum of, we call that S sub I, or S sub n, sorry, if S sub n, because we're going to n here. Don't confuse our indices and our ending value. So if S sub n is equal to the sum from I equals 1 to n of a sub I. So we're ending at n, and we're starting at 1. And then we're summing all of these a's together. And a sub I would be dictated by some sort of formula, but we aren't dealing with that just yet. So we have some formulas that can tell us the partial sums of an arithmetic series and a geometric series. So for an arithmetic series, we have the formula that S sub n is equal to some n. Sorry, that shouldn't be b. I was kind of fooling around with the indices here to make it less confusing, but S sub n is equal to n times a sub 1 plus a sub n over 2. So we're averaging these. So there's a very nice way to derive this, and that's really just you are listing out all of your numbers, and you realize that some of these numbers if you add like some of the numbers on the opposite sides of the number line, they all add up to the same number. So if you average it, then you can get a nice formula. And we also have for geometric series that S sub n equals a times 1 minus r to the nth power over 1 minus r. Okay, and r is the common ratio. Now, something that's important here is that we can look at an arithmetic series, and we know that for no value of n, even if as it gets closer to infinity, for no value of n, is our series going to diverge? Or converge, sorry. Because when you look at an arithmetic sequence, its terms go up linearly. It is a linear relation. So if you plot n on one axis and a sub n on the other axis, all of your arithmetic sequence or series and sequences, they're going to go up. So if you sum all of these, they're never going to be zero. The only case where you have an arithmetic sequence series that converges is when you have a starting value of 0 and your common difference is also 0. In that case, you're just adding 0 to 0 infinitely many times, and then you get 0. Now, for a geometric sequence series, it's a little bit different. And we're going to talk about this in the next video, because in a geometric series, you can have different values of your ratio. And for different values of your ratio, and you're raising n, if n is approaching infinity and you're raising r to the nth power, well, r might get close to 0 if you're raising this guy to a really small power. So in that case, our geometric series may converge. We're going to talk about the conditional convergence for the geometric series in the next video. That's going to be the main topic. But anyways, the point is, for an arithmetic series, you're not going to converge. For a geometric series, you may converge, and you can use that using this little partial sum guy there. Okay, so anyways, for the limit of a series, if the partial sum converges to n, it converges as n goes to infinity, then a sub n converges. So if I have the limit, as n approaches infinity of s sub n, that is equal to some value, L. Then we are going to have a converging series. That means that our sum as from n equals 1 to infinity of a sub n converges. On the other hand, if the limit does not converge to a number, so if the limit as n approaches infinity of s sub n equals infinity, then the series diverges. Okay, so that's just a little bit on the geometric series, the arithmetic series, and just an introduction to series and taking limits of these guys. In the next video, we're going to talk about the geometric series a little bit more specifically, talk about when it converges, talk about when it doesn't converge. And we're going to do a couple of examples. What you're going to notice in the series unit, at least for the first part, is we're not going to have many applications. Our applications are mostly going to come in the second half when we start talking about Taylor's theorem and the Taylor series, because with those we can approximate functions and use it to solve some problems. But for now, it's going to be fairly mathematical and abstract. All right, in the next video, we're going to talk about the geometric series. We'll see you then. Bye.